He kōna I purangi tēnei nā te reo irirangi o Aotearoa.
Imagine you're lost at sea. You've blown too far off the coast for your VHF radio to work, or for your mobile to get service. You've got a personal locator beacon, but you never checked that the battery was okay before you left. They only last for so long and you just forgot. It sits beside you, dead. And now you're drifting into the vast expanse of the Pacific Ocean, hoping that someone comes looking, hoping that they know where to even start looking. At night, you can see fast-moving pinpoints of light pass overhead. Satellites orbiting the Earth. If only there were some way to signal them. Kia ora, nau mai haramai ki te ao hurahanga, kōklek and kanantenei. Today, we meet a team trying to crack this.
How do we save the most lives at sea? Fundamentally, for Ella and I, that's what drives all of this. That's why we're doing it.
This is Dr. Tom Dowling, and we're standing at the edge of Mission Bay Beach, just a short drive from the University of Auckland, where Tom works as a lecturer, specialising in Earth observations. Ella is Ella Faciana, a new graduate who's been working with Tom as a research assistant on this project. We're here so he can show me their latest search and rescue prototype in action out on the water. A low-tech core flute device, the shape of two slightly offset back-to-back triangles, each made by joining two wedges together. It's been carefully designed, with aluminium-lined corners to funnel satellite radar, and a loop of plastic at the bottom to act as a baffle.
That's a bit chilly. So you can see as we drop it down onto the water, you can see the baffles filled with water out underneath, and they keep it, and it just sits on the sea surface like that. It just floats along. And even though it's quite windy today, it's not being flipped over. Like, that's quite a strong breeze that's coming through now.
Yeah.
You can feel that, and the previous square designs that we had earlier, they would have been at greater risk of flipping and even possible collapse. But you can see now with the way that we're doing things, thanks to Ella's brilliant ideas, there's no water getting onto the surfaces, it's just sitting here, it's not flipping over, and having a good old radar time.
New Zealand is responsible for a search and rescue region of about 30 million square kilometres of ocean, stretching from Antarctica to north of Samoa, a huge arrow-shaped slice of the southern hemisphere. When boats go missing without a way to communicate, it's fully a needle-in-a-haystack type situation. Narrowing down that search area using something that radar satellites could detect would be a massive help. Something that you could carry on board, then unfold on the water and tie to the back of your boat when you got into trouble. Hence, the SAR4SaR project. Most of the design work and prototype building on SAR4SaR has been done in the University of Auckland's Space Institute Lab for Fabrication and Assembly. It's there that I meet Ella and Tom first, and he explains the doubled-up acronym.
SAR4SaR is a joint project with the New Zealand Defence Force, and in particular Defence Science and Technology, and it's their name, so they get full credit for that cunning name. Because what the name stands for, it's Synthetic Aperture Radar for Search and Rescue. So it's firing radar down from space and finding people lost at sea.
And synthetic aperture radar, not something that many of us will have heard of. What do those words mean?
Sure. So SAR is this really cunning technique. I think all of us are perhaps more familiar with the radars that we see rotating on the top of air control towers and on a big ship and that kind of stuff. And the thing with radar is you need a big antenna to get a better resolution view, to get a higher resolution view. Now, you can't put a big rotating antenna on a spacecraft or an aircraft for that matter. So back in the 50s and 60s, they came up with this very cunning idea where you use the motion of the aircraft to create the length of your antenna. So the synthetic aperture part of synthetic aperture radar is the way in which we create a giant kilometre-long antenna due to the motion of the spacecraft or the aircraft to let us do this really high-resolution radar work.
Okay, so that SAR part is a satellite that's flying in space, that's beaming down radar, so electromagnetic radiation, and you're hoping then to design something that this satellite will be able to measure, pick up, kind of ping when it's lost in sea.
Yes, absolutely. So ping's a good way of doing it, or talking about it, sorry. And the key thing here is that we're exploiting some really neat fundamental physics, which is these are corner reflectors. They're trihedral corner reflectors. And this is a function of that electromagnetic EM radiation, that as it comes in and hits a surface, it will bounce if you've designed that surface correctly. And if you have three surfaces at 90 degrees to one another, what you get is this huge magnification, essentially, of the energy return. All the radar that's hitting it all gets collected, and all of it gets bounced right back to the satellite, which creates a really, really bright spot, almost like a flare. It's the radar equivalent of lighting a flare and waving it above your head. It just makes you super visible. Also, because it's on the sea surface, you get this glimmer effect because the three surfaces are moving all the time. So not only is it a really bright spot, particularly on the ocean, which is why it works so well at sea, you get this kind of bright sparking flare. It literally looks like a starburst in your radar image, which is much easier for us to detect than anything else.
So the foil-coated corners are key to the satellites being able to ping this device. The question then is how to get the shape just right, because they have quite tight design restrictions. It needs corners, ideally facing different directions. But it also needs to be something that will fold down to be flat and small, easily tucked away in the corner of a boat. And then it needs to also unfold quickly in an emergency. Plus, it must be something relatively cheap to make, but also waterproof and durable enough to withstand rough seas. And so, with all of this in mind, Ella began with bright-coloured small squares of paper.
This is where we started, basically, with just paper and tape and the origami YouTube tutorials. This was kind of one that had the initial closure pop-out idea.
It kind of looks like the fortune tellers I used to fold as a kid. I'd pop them on my fingers and flip back and forth, and there would be answers hidden under little flaps. It's in a plastic lunchbox full of different small shapes folded in coloured paper. If anything looked promising, Ella would draw it up in CAD, computer-aided design, and then use that in a computer model that would tell her whether the shape would lead to that starburst effect or not. It might seem low-tech, but it worked for Ella to get going on the problem.
Starting with paper was really easy to just work with and really quick to assemble, really. And since they're so small, if I have an idea, I can just, I have this little thing of origami paper that's just a bunch of squares. So that was a really easy starting point, and the materials that we knew we wanted to use had to be super inexpensive and easy to assemble, which translated to core flute and duct tape.
So from this box of paper origami shapes, over here on a bench is some core flute and duct tape, with a little bit of a measuring tape inside.
Yeah, so the tape measures there's two of them in there, placed back to back, or insides to insides. And they fold down the same way that this origami shape. So you can kind of see the translation.
Right, it was sitting as an open cube up on top of the table, and now you've folded it twice, and it's a flat little square once you've done that.
Yeah, exactly. And the tape measures on the inside kind of act as a spring, because the tape measures, they want to be flat. So when they're folded, it has that potential energy just waiting to just
snap out.
Yeah.
There have been several prototypes along the way. One involved 4 full cubes linked together and made waterproof with a plastic cover. This was tested first on land and then brought down to Campbell Island on a Navy ship for testing down there.
What I'm holding in my hands right now is our first attempt at that then came down to the Southern Ocean with us on HMNZS Canterbury. We've put those cubes together. They're in what we call the caterpillar configuration. So it's a set of offset cubes, because that makes it easier to fold down.
Each of the cubes are 38 centimetres by 38 by 38. And when stored, this prototype can fold down to the size of a single square side. So 38 by 38 centimetres.
And then it folds out, as we will now demonstrate. And as we fold it out, it's got quite battered, and it's a very early prototype, and it smells a bit due to the having been sitting on there. There we go. And the spring's a bit old, but it pops out. And now you have a radar reflector. So what we have now, what looks like it is 4 full cubes, arranged 2 and then 2, offset slightly from one another.
This test, in the subantarctic region of the Southern Ocean, was helpful for 2 things. First, to test the radar pinging at higher latitudes.
We want this to work all around the world. So we'd shown that the basic idea works over New Zealand, but as you go up through the higher latitudes, the angles change. One of the things we don't have really any control of here is the angle at which the radar's looking at the radar reflector for all sorts of reasons. So this was to go and test it at those higher latitudes.
And the second thing they wanted to do was to stress test it in tough conditions.
It had been too rough for us to stay at anchor in the fjord overnight, so we'd gone out during the high winds overnight, had a very rolly night at sea, and then as we came back in, it was still quite strong winds, and we were dropped off the side of the ship whilst the ship was in motion in a Zodiac, launched off the side at speed ahead of the ship to then deploy the reflector for both the ship's radar to look for it as it comes in, because if people are lost at sea, you want ships to find them as well, and to then test it in these higher winds with a satellite overhead in the mouth of the fjord where you're more exposed. And yeah, the gusts were up to 50 knots, which was spicy, it's fair to say, and these things were spinning around like crazy, which then led us to realise, we need to add some more design elements to help keep them more stable on the sea surface. So the next generation of designs, we then developed what we're calling the sea baffle system.
Their next big design change also came as a direct response to field testing. In June and July, they did a series of tests at Omaha Beach, north of Auckland. It was extremely windy, said Ella, and the cubes were collapsing. So overnight, they workshopped and came up with the idea to reduce the cubes by half, by taking away the outer walls and the top, making a 3-sided wedge shape.
Like an open-faced bucket, almost, is one way to think about it. So any radar wave that comes in and hits this surface, much like a funnel would collect rainwater or something like that, it collects it all, but instead of funneling it out and down, like an actual funnel would, it picks it all up and bounces it right back to the sensor.
With the offset caterpillar configuration, there are radar reflecting corners facing each direction. And the new half-cube wedge shape, with its baffle, was more able to withstand strong wind. These field trials were a pretty intense time for the 2 of them.
Ella and I worked, I think, 3 weekends in a row, so it was just 3 weeks non-stop with no break whatsoever. Back out on the water, cool. That mechanical fix worked. Great, build another set of test versions, and then out on the water for the big final trial, where there was also the Royal New Zealand Air Force flew their search aircraft over it as well as the University of Auckland research vessel looking for them, as well as all the satellites looking for them. So, that's a lot of people doing a lot for us. We really want to have something that works, and I'm very pleased to say that after a very stressful month or 2, we did have something that worked spectacularly well.
I got a picture through of the snap that they got back from the radar satellite, and you could very clearly see the bright spots on the water.
This is Dr. David Galligan, Director of Defence Science and Technology, or DST. And he's talking about a picture that originally came from Paul Garnham, the DST scientist who's worked closely with Tom and Ella on this project.
And I talked to the guys who'd just been out there doing that experimentation, and I'm told there were tears all around. It was such an ice-breaking thing where they really achieved something. They were really looking forward to the end of the week when we brought some senior people, including myself, down to take a look. And they were in that space where they were actually able to claim real success with the trial and demonstrate that viscerally to us. So all of that tension that had built up over the time that they've been building these prototypes and testing them culminated with that really great outcome.
DST is a New Zealand Defence Force team of about 70 people working out of the naval base in Devonport, with the goal of increasing how effective the military is. And because the Defence Force is involved in the search and rescue response across New Zealand's ginormous marine area of responsibility, the DST is interested in making this job as efficient as possible.
New Zealand has an area of about 30 million square kilometres that we need to cover for search and rescue. Defence Force has a range of assets, aircraft and ships and the like, which can help the government cover its requirements there. It's incredible, the area that we have to cover with the number of people in the country, the number of assets Defence Force has, but we do a very credible job of covering that area. And we're always striving to find new ways of doing things more efficiently both to preserve that limited number of assets that we've got, which will never be enough, in inverted commas, as it were, but also to be more effective wherever we can be at assisting and finding stricken people and vessels as quickly as possible.
It's the Rescue Coordination Centre New Zealand that's responsible for organising search and rescue efforts. And whether the Defence Force gets called in to help and what they deploy depends on each event. It can be short-range aircraft or ships, but an important Defence Force asset used to search for those lost far out to sea are their long-range planes, P-8A Poseidons.
We were alerted by Kiribati and Fiji search and rescue authorities after the men were reported overdue while travelling between two islands.
This is a video featuring Taylor Monaghan, a search and rescue officer at the Rescue Coordination Centre, describing the rescue of two Kiribati fishermen who were lost at sea for almost a week.
On day 5 of the search, the Poseidon spotted the men in their boat. A local vessel then picked them up the next day.
The fishermen were lucky, because without transmitting functions on board, this is how searching goes. Drift modelling to guess where wind and currents would have taken the boat, and then flying a P-8A over the area to try to spot them.
Yeah, that can take quite a time, which is going to cause risk for the people who are stricken at sea, and also with our limited asset times, etc. Effectively, we can do something more useful with that aircraft if we can limit the time it has to actually just patrol looking for these relatively small targets in the middle of a big ocean.
Plus, these planes are not cheap to run. David's primarily focused on New Zealand's area of responsibility, but he sees the wider potential for these radar reflectors.
There's almost unlimited scope for this kind of technology to be used for around the world, in fact. It's got great hopes of success, I think, well beyond just our region.
In March, Ella Faciana travelled with David to the Pacific Operational Science and Technology Conference in Hawaii, where she explained the project to people from other countries who were quite interested. One particular conversation stood out to her.
One of the guys from Tonga talk about how a lot of the technical solutions that other people would bring to the little island is that it's expensive, it's not repairable, and once, for example, the EPIRBs, once the batteries are done and they need to get rechecked, shipping batteries in is really difficult because batteries are hazardous goods. So keeping that in mind, we wanted to make sure that it was super robust in terms of you get one and you have it till you use it, and super low tech, so there's nothing to maintain and it just sits there.
So the low tech aspect is attractive to many. But another reason these reflectors could be very helpful is because they can also be spotted using regular radar. Here's Dr. Tom Dowling again.
This is the really cool thing about it, is that this makes you visible to all elements of the search and rescue chain. So we've designed these to be seen from space, and that's what they're specialised for. But because we've achieved that, it also means they're super visible to maritime search and rescue aircraft with their radars, and it's also pretty visible on just a standard, very Billy basic civilian yacht navigation radar. Because the University of Auckland research vessel has a basic navigation radar on it, and we were able to see these reflectors bobbing around on the sea surface out from about 1.5 nautical miles. So the satellite can tell people where to go, and then the aircraft makes that search box even smaller, and then even in the dark, even in the cloud, in the fog, a boat can then find you as well from a distance. So the distances you can be seen from change from the many, many thousands of kilometres of space, hundreds of kilometres for the aircraft, down to a nautical mile or two for the vessel.
We've been talking so far about one side of this equation, the radar reflector. But there's a second part, the SAR satellites. Which ones are they using?
We are using every single possible satellite we can. I think we achieved basically every nation who runs a satellite that is, within, let's say, the Western sphere of influence, was looking at these. So we've had our European partners looking at it, Canadian and American. We also had South Korean at one point as well, because the thing is that you need a satellite to be in the right place at the right time to find you. One satellite is coming back around the same point on the Earth, typically, for this sort of mission, about every 6 to 12 days. So what happens to you in the rest of those days? Well, you need other satellites looking for you. So we were testing to see that you could see these in everybody's satellites, which, again, it achieved quite nicely.
The data from the satellites is analysed to essentially produce an image of what it's picking up. And the shape that results in this radar starburst is designed to be quite distinctive. But might the satellites mistakenly pick up something else?
There are two things that can create a kind of false positive similar signature out in the environment. Now, basically, you don't get three surfaces like this next to each other unless you're in very rocky areas like mountains and that kind of stuff, or sea cliffs. But we're out at sea typically with this, so that's not the problem. The two things that cause us potential problems are sea ice. So we're actually collaborating with a Danish group who also had a project named SAR4SaR, it turns out. We've now joined forces and teamed up. They have a very similar problem set out in Greenland with the Inuit communities out there. And then the other common one is you get this effect called wave lensing. So we have waves on the ocean surface, and particularly if they start to break, or it's particularly in rough weather, the surface of the water can create a similar effect. It is much less bright, so we're pretty confident we can handle that fairly easily, but it is still a piece of work that we need to do.
This is what Ella is hoping to investigate next, as part of a PhD project. Out on Mission Bay Beach, with the Pacific Ocean out on the horizon, Tom reiterates that the aim isn't to replace existing tools.
One of our mantras of this project is this isn't your only way of being found. This is very much your last line of defence, or it's your way that is available to you when nothing else can be used. Because you do have other methods. So you've got EPIRBs, which are electronic personal radio beacons, where you pull the tab and then it will ping off to a satellite or to something else. It's an active beacon that's saying, come help me, come help me. They are fantastic. We're not looking to replace them. They work really well. So these reflectors are an additional part of your kit, in addition to a sat phone, an EPIRB, a VHF radio, the stuff that you would normally have. It's in that same kind of category, I would say, as a flare gun. You send up a flare, but it's one that can be seen from space.
What's the first resolution that you get from the ping off the satellite? I mean, is that like they are in this, 100 square meter patch of the ocean, or is it finer tuned than that?
So we're very lucky that we have from space a range of platforms that actually have a pixel ground sampling distance, so how much distance on the ground an individual pixel in the radar image covers, of anywhere from 15 centimetres up to about 10 to 20 metres. So typically we would search with a radar that's got 10 to 20 metre resolution, or maybe even up to 50 metres. These can still be seen because they're collecting their energy and returning it back. They're much fainter, but they can be seen. And then you use one of the high resolution radars to go, cool, let's search this smaller box, which is probably a couple of 100K at that point, and then we go, cool, at this time when this image was collected, we know this person was literally here. Or more like we'll end up in a situation where we go, this is a really strong return, and then there's here 3 weaker returns. Our modelling and our math says it's probably this one, but you should check these 3 as well. And it's a precise position. Now, there is, however, a time delay. So this is the thing we need to work on with the satellite companies still, is how quickly can they get that information to us. Because the quicker they get it to us, the more precise that position to search is. What we will need to do is combine this with what is actually used already in the SAR world, search and rescue world, which is drift modelling. So what we'll be able to do is say, this was their position an hour or 2 ago. We think we can get it down to an hour or 2. They have probably drifted to this area. Therefore, your search box, it isn't 20 metres, that would be a bit too easy, but it will end up in the region of a kilometre or less, I would say.
And in terms of getting the data from the satellites, I mean, is there some kind of international collaboration between those who are flying satellites in low Earth orbit with this SAR on them that you can say, hey, you've got a satellite in that area, please can I see what it's seeing?
So that is something that we're working on as well. So there are what I would describe as a patchwork system at the moment. You can contact companies individually to see what's going on. We've also got, for example, our Canadian partners are fantastic folks, because they will, if you've got someone lost at sea and you tell them that, and then you tell them roughly where you want them to look, they'll do it for free, and they'll just do it as a humanitarian assistance. So great, Canada's on board, we can do that. With the commercial companies, obviously it's slightly different, and we have to work with them to find ways to support their enterprise, because you've got to pay for the service, but also to get that really quick data really quickly. So we're still working on that and exactly how that would look like.
So, still a bit to figure out. And while the plan for the devices is that they will be low cost, there will be a price to access and analyse the radar data. Significantly less than the cost of flying a plane around to look for a boat at sea, though. There are many next steps. Figuring out more durable materials to rebuild the core flute and duct tape prototypes, and problem-solving how to manufacture the devices in a way that keeps them affordable, plus spinning out a company to facilitate that. And then, again with the DST, testing this next generation in further real-life settings, far out to sea, in a true search and rescue scenario. Tom once served in the UK Navy, and he's happy to be working on such a practical project that brings together his expertise in remote sensing with his love of all things maritime. He's happy too that other maritime folk are responding positively to it, internationally, but also locally, like the crowd at this year's New Zealand Coast Guards conference, where Tom gave a talk about the project.
It was real validation of the approach. Everybody in that room went, oh yes, please. We can see this immediate use case. We can see it helping in everyday operations. If people out there had this, we would be able to find them much faster and much more easily. So it was really comforting to know that we're doing something on the right track here.
Thanks to Dr. Tom Dowling and Ella Faciana of Waipapa the University of Auckland. And to Dr. David Galligan, Director of the Defence Science and Technology Division of the New Zealand Defence Force. This episode was produced by me, Claire Kincannon, and sound engineering was by William Saunders. Production help was from Kate Newton. If you've enjoyed this episode, then you should definitely check out RNZ's brand new podcast called Search and Rescue NZ, where host Paul Roy explores some of New Zealand's most gripping rescues. Tēnā koe I whakarongo mai. Thanks so much for listening. I'm Claire Kincannon. Have a great week. Kia pai, the wiki.